Thank you very much. Okay, and now I just want to share this. This is something from the information I received. I think yesterday you had a very, I understood you had a very important, interesting case study presented by Mr. Constantino, and you had a very nice discussion. I will discuss separately with Dr. Carlos and see how we can use part of the discussion to in our exercise also. Okay, so this is the and this is already covered. I will not go into detail. I also, this is the picture I got from different sources. You see, this was the data I received from Funai consultants from Funai. So I think this one we'll talk a little later. Okay, so this is fine. So case study will be I mentioned will be presented because this was presented by Mr. Constantino Cecela from Funai, and we will work on this. We will use that for our exercise and for our other activities thing. Okay, now what I would like to do is I would like to now move to actually, I'm a little bit running behind time, so I would quickly go here. I would like to start with the introduction of some of the components of civil works. Okay? And in this part, we have about half an hour remaining, or less than half an hour, less than 20, let's go up to 12:15. So we have about 25 minutes, so 25 minutes. So I would like to...
Because you can actually proceed up to 12:30.
Okay, thank you so much. That is very nice. So I have about 40 minutes. So I will go up to 12:30. And I would like to, because I want to make up for this little bit lost time, and I want to introduce some of the civil works, okay? I will start with, this is the outline. Although for mini hydro projects, we are not going to build big dams, yes? But I think as planners, you have to also understand some of the concepts of designing or planning for large projects. So I will talk a little bit, give it some examples of dams. Then I will go to from part 2, from the headworks, weir, intake, settling basin, tunnels, pipe flow, canal, penstock. I will introduce you some of the computational, the hydraulic design part. Okay, just introduction. The real exercise, we will do it in December and January. And I don't know, I will discuss with you all. I have some Excel-based small programs where you can put the data and the design can be done. So we do not have, everybody doesn't have laptops here, but I will try to give that early. So it may be an exercise for you to practice. Then we can discuss the results and the procedure in the classroom. So that we'll plan. But today, just to give you an idea of how these different civil construction, civil works, as you know, there is civil works, there is electromechanical, hydromechanical thing, and civil works, depending on the project, can be 40, 50% or 70, up to 70, 60, 70%. For large hydros, civil works component can be high. For mini hydros, it is maybe, I think it's about 50, 45, 50, 60% of the cost. Okay, now I think it's important we understand what a dam is, okay? And of course, there is a lot of controversies about dam, okay? But you have a Kahora Dam, and maybe you have, I think if I understand, there is some plan for EDM and for Mozambique agencies to develop some more dams, maybe in Zambezi and other places, but it's good. And these dams can be small dams and large dams, big dams. So what is a dam? Dam is a barrier across a river to store water in upstream side or to raise water. Just because you have a dam doesn't mean you have to store a lot of water, but you may want to raise the water so the head increases, okay? So because if you have a narrow valley or something, you can do that. Storing water has its own part. What does it function? It functions as to store water and to build up head. So what are the different components of a dam, okay? Now, for example, you can have a dam. On top of the dam can be, you can have a bridge. It can act as a bridge from one place to another. You can go over the dam also, okay? And then the dam basically has, it has, this part is called the hill, the front base, and the end base, the downstream side is the toe. The sluiceway is a, basically is a pipe or a thing, conveyance system where water from the dam flows downstream. And this can hold the turbines, sorry, the penstocks and the pipes that will go to the powerhouse. The maximum water level is here, okay? And above this maximum water level, you have what is known as the spillway. And you can have a spillway inside the, if you have it inside the dam, just there is a, you can have a, any excess water just flows over the spillway. Then this area is the normal water level. And so you have not the maximum water level is a little bit higher than the normal water level to sort of do store flood water and do flood attenuation. You know, by flood attenuation, what I mean is you lower the peak flood, because the peak flood, let's say, is 5,000 cubic meter per second. By storing part of the flood and then discharging, you can like reduce the peak flood from 5,000 to 3,000. This has got other benefits, okay? And gallery is the, sometimes you have a gallery to sort of see the, what do you call, from operation maintenance and the other thing of the monitor the dams, okay? So this is the thing. And what are the different types of dams? So I'm getting a little bit theoretical, but please bear with me. I'm just trying to introduce you things. Now you have dams of different types, of different functions, okay? You have a storage or a conservation dam, a diversion dam, a detention dam, or a coffer dam. So storage dam is, and conservation dam, it stores water. Diversion dam is like a where it just diverts water. Detention dam is, it stores flood water and reduces the flood peak downstream. So it's used for flood protection, flood management. Coffer dam are temporary dams that is built when you have a construction going on, let's say, or even a bridge or another hydraulic structure across a river. You build a temporary dam called coffer dam to divert water temporarily during construction period. Okay, this is the based on the function. Based on the construction material, you can have dams of concrete. You can have earthen dams. You know, sometimes concrete dam you have when you have a bedrock which is close to the bed level. If the bedrock is not there, then concrete dams may not be feasible, so may not be technically sound. So you have earthen dam. Then you can have masonry dam. You can have steel dam. You can have timber dam. Dams made of timber, rubber. Basically, timber, rubber dams are small dams. Steel dams are smaller dams. But if you have large high dams, it's basically concrete or earthen embankments or rock fill dams, okay? And based on the structural load transfer, you can have a gravity dam. Gravity dam basically is based on the weight of the dam. The weight of the dam will sort of control the load, okay? So whatever, this is like, for example, the gravity dam here, this is, so whatever hydros, because when you have water upstream, the load that occurs in the dam is horizontal. This is the hydraulic pressure, hydraulic load. So based on the depth of the water, because it's basically triangular at the base, its head multiplied by gamma. Gamma is the specific weight of water. Gamma H is the hydrostatic pressure, so called. So this is counteracted by the weight of this concrete structure. So this is what is known as gravity dam. Arch dams like the Kahora Bassa Dam, what it does is it's a curved dam which the water pressure sort of, when you have a curved arch dam, the load is transferred into the abutments on the side. When you have good rocks on the side of the dam side, on the slopes of the thing, then you have built arch dams. Buttress dams are basically dams which are concrete and they have buttresses, so-called sort of supporting buttresses like retaining walls that support these dams are called buttresses dam. Other classification of dams are, some dams are overflowing dams. You can have water flowing over the dam. Some are non-overflow. Earthen dams cannot overflow because if you overflow, the earthen dams breaks. Concrete gravity dams, you can have some overflow without much damages, okay? And you have low head, high head, medium head, rigid, non-rigid dams, other things. So you have basically buttress with concrete timber, earth and rock, embankments with, you have basically an earthen dam with a impermeable core. And basically what it does is, it basically there is a phreatic line, the water the water level on the upstream, the water pressure is slowly sort of thing by the end in the downstream by the toe, the water pressure is minimized. So this is on from the section view is this, top view is like this, okay? From the, when you look at it from the top, this is the arch dam, this is the buttress dam, this is the earthen dam. The volume of material used in an embankment dam is of course higher than in the gravity concrete dam or masonry dam, because the cost of this concrete is more than the earthen and rock dam, but the volume is more. So this is these are the trade-offs that you have to consider when you plan or design a dam. This is just a general overview of the types of dam. Okay. Now I just like to take you around the world. For example, the Rockfield Dam here is you see, like this is the Moala. I mean, I just took it from different sources from Lesotho, very close by. So I just put in a Rockfield Dam. One thing you have to be careful is in the earthen dam, the spillway cannot be at the part of the dam. So there was a possibility of having a spillway. This is on the right here is the spillway. Okay, let me just use this one. Okay, this is the spillway is on the side over there. This is the rockfield. It's basically a dam like this, an embankment dam, but with rockfill, and there must be an impervious layer, earthen rock. The Kahora Bassa Dam is basically an arch dam. Okay, so basically it is something like this. There's an arch. All the pressure, the water pressure coming here, sort of all the load is transferred to the side abutments, okay, on the side. So you have a good rock outcrop here, good sound rock. So they do that. Now this is the spillway sort of thing. Okay, anything extra, it passes through the dam also, Kahora Bassa Dam. Okay, and this one is a Hoover Dam. Hoover Dam, I just wanted to put it here because it's a very famous dam in the US, in Grand Canyon, I think somewhere there. And you see, they have this is from satellite images. It was made in 1936. It's 222 meters. Okay, it's also an arch dam, like a Kahora Bassa Dam. Okay, you see, this is the pressure is here, and these things are the intake are more or less. They have I don't know what, I forgot exactly the name of this. It's called Morning Glory, and so intakes are here. So it's a famous dam in the US. Okay, buttress dam is basically supported by buttress. You have a steel dam like this. Okay, you have so you have steel structures, and you do a trusses and everything. You have anchors and you have footings. Then you sort of all the steel, and there is this steel support in the anchors that it's like a truss design. Timber dam, I use local material just to raise a dam. It's a dam. So this can be used. A timber dam well will be cheap, but you may have to repair it every other few years. So for a mini hydro project, this type of dams might be a good economic consideration also. But of course, it depends on the material available and other factors. Okay, and the Grand Ethiopian Renaissance Dam on the Nile upstream basin, This is a famous dam that Ethiopia is now building. And I think there is some transboundary issues. I don't want to go into details of it, but I just wanted to show this was a nice picture that was, this was available in the one article on National Geography, or I think it was National Geography. Actually, it was written by somebody I knew. So I just wanted to share this picture. Okay, now, and with satellite images, you can see how, I don't know if it has been commissioned, they are about to fill it or something. So basically they look at the, I think different, if you see March 24/7, June, July, recently, March. So it's basically, they've started filling this dam, but I also see a lot of sediment in this thing. But anyway, this is just a, I just wanted to introduce you, and there's a lot of issues, transboundary issues and other things. I don't know the details, but I just wanted to show you that. Now, the highest dam in the world, it's in Sichuan province, China, Jinping. It's 350-meter tall. It's an arch dam like the Kaurabasa. And this is a friend of mine had taken this picture. I think he went to, when he was there, and just see such a nice picture from the downstream side, okay? And I think the next one is the famous Three Gorges Dam in Yangtze River, China. This is the largest hydroelectric project. Just imagine, 22,500 megawatt. It's 108-meter high. The cost was 59 billion US dollars. It took 17 years to build. It relocated, resettlement involved 1.3 million people. The reservoir area was 1,045, to be square kilometer, and this is in China. Okay, so just imagine the total potential of Mozambique hydropower potential is considered about 19,000 megawatt, but this single project produces 22,500 megawatt. It also has flood control benefits. I don't know. I mean, I don't want to go into the social, environmental, economic aspects of this dam, but this alone, I just wanted to point out, is a hydraulic structure of immense size, and that I think few countries can make it. Okay, and there's, just imagine the amount of money spent, time, and the it took to build this is also 17 years. It's not a joke. Okay. Okay. That is just a brief introduction to the types of dams and some of the dams, large dams. So, I mean, as I mentioned, not all of this will be applicable for mini hydro projects, but as an introduction to hydropower and dams, I just wanted to give you these, just an overview of these dams. Okay. Now, I would like to, okay, is there any question, specific small questions that I can take, you want to ask now? I mean, obviously I did not cover anything very technical. It's just an overview of the different types of dams. Carlos, any question from anyone or comment?
Thank you, Divas. Alguma pergunta, algum comentário, colegas? Antes de prosseguir. Alguma pergunta, algum comentário? No, Divas?
Yeah, okay, thank you. Yeah, no problem. No, just, I think there was nothing much. Okay, now I will go into some design aspects. It's basically a hydraulic design aspects of a gravity dam. Okay, because it helps you, because this is also, it helps you to design your wear. Okay, and basically in a dam, a gravity dam, as a civil engineer, a hydraulic engineer, like what it has to do is, okay, you have to hold this much of water upstream basically by the weight of this dam. And this dam is normally of this sort of a typical cross section here. Okay, now what are the forces acting on a dam? Okay, now the main force is, of course, the weight of the dam. the weight of the concrete. Okay, so the volume of concrete and the density of the specific weight density of the concrete will give you the weight. The weight acts towards the vertically down. Okay, and what is the other important force acting is the water hydrostatic pressure. The water pressure is you have all this water, volume of water, this will act, horizontally, it will act from here. Okay? So on the top, the water surface, the pressure will be zero because this is atmospheric pressure. But when you go down, triangle like sort of a thing, it basically gives you the forces acting on the vertical side of the dam. Okay? This is what is known as the hydrostatic pressure. And the other force is the upward pressure due to water percolated under the dam. So there will be some percolation of the water from here, and this will also create an uplift pressure. So it will try to overturn the dam unless, so it is balanced by the weight of this dam. So it's acting vertically up here like this. I'll show you how. Then I don't know how earthquake prone is Mozambique. Probably it is not so much. Then if it is an earthquake in a zone like Nepal, China, and other countries, Turkey, Western USA, these are very highly seismic active countries. So in Nepal, we have to, when you design a dam, we have to make sure that our design is safe from an earthquake perspective, because earthquake can have, it can move vertically, horizontally on both directions. So so too rigid structure may not be. You have to have some flexibility. But anyway, this is a structural engineering perspective, but you have to consider an earthquake pressure. There is also a wind pressure. Large dams there is high wind. So the wind can have problem. So which has to be also considered. And there is a wave pressure also. The water surface, there is a wave, and sometimes this wave can also act on the dam, which the dam has to be able to manage. And then, of course, there is some silt. So on the lower portion of this thing, normally they have some silt accumulated. So this can also create a silt pressure. So basically, these are the forces acting on a gravity dam, which has to be taken care of. Okay, now how is the weight of the dam calculated? Okay? So this is the cross section. So basically, the weight of the dam is the major resisting force. All other forces are acting on the dam. It's basically horizontally acting or vertically upward acting. Weight is the dam is vertically, it is downward. So it is trying to counteract all the loads that is acting on the dam. So basically what you do is you find the weight of W1, W2, W3, you do in section, you find the area and the unit length, and you multiply that with the specific density of concrete, then you get the weight of the total weight. And the weight acts, and the CG, the center of gravity of this section, the center of gravity of this section, the center of gravity of, it's basically in 2/3 of here, 2/3 from the A, 2/3 here, the thing. And basically you calculate the weight of the dam. So this is plain and straightforward. The water pressure, because this is important, the water pressure, as I mentioned, is you have a cross section like this. So basically the major external force acting on a dam is the water pressure. On top of the dam, on the surface, there is an atmospheric pressure. So the pressure at the surface is zero. Pressure at the base is gamma H. Here I put gamma W because it's water. Gamma W is the specific weight of water, which is equivalent to 9.81 kilonewton per cubic meter. So what the pressure it acts is 9.81 times the height. Okay, and it sort of in a triangular way. Okay, and it acts because the center of thing will be H is the upstream elevation of the depth of the water, so H by 3. So that this area of unit is half of gamma H square, because half gamma H is the force here, the area here, this is H. So this is, and P acts at H over 3. Similarly, in the tailwater side, there is a force acting if the water level, tailwater level is here, force acting from the opposite direction here. And there are vertical components of the water, the pre-vertical, the PV1, which is basically the weight of water and the volume of water acting at the center of ABCD and acting at the center of this one. So this is the hydrostatic pressure calculation. Okay. Now the uplift pressure, okay, the uplift pressure is due to the seeping water under the dam. So there is some seeping water under the dam. So on this section, the seeping water is uplift pressure at the head of dam is gamma H. Uplift pressure at the toe of dam is gamma H dash. And there is an uplift pressure. There's a break of the thing because there is a drainage gallery here. So it's basically, this is the empirical formula they use. So it acts in this manner. Okay, so this is the other force that acts uplift upwards vertically. Okay, and the earthquake pressure, I mean, just give you an example. This is more of a structural thing. Effect are in two ways. It affects in the vertical direction as well as in the horizontal direction. If it's not designed properly, these dams can break or collapse, and it can have catastrophic damages downstream, because these dams may be holding a lot of water. And when this dam breaks, and if there is a release of all the water quickly, it can create flooding and other problems, damages of debris flow, and so much of water flowing in such a short time that can have huge loss in the downstream portion. So effect of vertical inertia force, alpha W, is developed on the dam. The direction of the force is opposite direction to the acceleration. Hence, unit weight of the dam and water get altered as follows. For dam material, for water, this is the thing. From an horizontal direction, also there is inertia force in dam, hydrodynamic pressure of water, because what it does is it uses the volume of the dam, the volume of water, and pushes it in different directions. You see, so it's not, if it's air, it's all right. But the inertia force is the mass of the dam and the acceleration due to the earthquake. You know, the weight times acceleration due to earthquake. The hydrodynamic pressure due to earthquake is basically, they say it's in an elliptical parabolic thing. This is how it is calculated. I will not go into a detail because this is a very technical issue that needs something, but I just want you to know that the earthquake, in earthquake prone areas, this is also another pressure and load that the gravity dams have to be designed for. Okay, now the other thing is the silt pressure. Okay, silt pressure is you have silt accumulated in the upstream. When you have the storage of water, there is silt. No? There is this sediment that accumulates. So this silt pressure will act on this dam also. So this is the silt deposit upstream of face of the dam, the silt pressure. This is the formula they use, and the angle of internal friction, height of the silt deposit. And these are, I mean, you can refer to standard textbooks and design manuals, which gives you the values of the internal friction of silt and other things which can be used, but you have to consider the silt pressure. And the other one is the wave pressure. That is, a wind wave will create so waves in the river. You see, this is the waves in the reservoir due to the wind. Forces to the wave is given by this equation, acting 3/8 of HW, okay, above the reservoir level. Okay, it acts here. HW is height in m from trough of wave to the top. From here to the top, value of H is calculated in this way, and these are the formula given, and uh, uh, um, uh, and this weight has to be also calculated, because when you have very high wind and the wave generated, then it can have a major load on the dams also. Okay, now, okay, these are the loads. Okay, we talked about the different loads of the dam. Okay, the weight, the hydrostatic pressure, the uplift pressure, the earthquake pressure, wind pressure, wave pressure, sill pressure. Now, you have the load in different directions. So when you do the stability analysis of the dam, when you design the dam, when you size the dam, when you decide on the dimension of the dam, okay, what should be the base width, what should be the slope, everything, okay, this is will depend on these stability analysis. One stability analysis you do is you have to find the factor of safety against overturning, okay? Because you have a hydrostatic forces here, you have the uplift forces here, you have the weight here and other forces. So you have to do what is the resisting moment and what is the overturning moment is here. The resisting moment is by the weight of the thing. So you have to calculate this, and you have to get the ratio between resisting moment and overturning moments, and the factor of safety is the resisting moment should be 2 or 3 times more than the overturning moments. And I think this one, you know the loads, you know the forces acting, you can calculate the moments here. Okay. The other thing for a stability analysis is the sliding. Okay. Because of the pressure, because you have the load on the dam, okay, because there's a foundation plane, there's a gravity, there's a slip, and this is, so you can really have what is known as the sliding effect occurs when the net horizontal force exceeds the frictional resistance developed at that level. So basically, when you have a dam based on the base, there is a frictional force acting on from right to left, and there is the hydrostatic pressure acting from left to right on this direction. So this can cause an uplift thing when pressure, and which is given by this formula, and the factor of safety should be more mu the vertical and the horizontal. No, the vertical load friction and the horizontal thing should be, and so mu is a coefficient of static earth pressure, which is between 0.65 to 0.7. So you have to basically make sure that the stability analysis in terms of sliding is the factor of safety is more than 1. Okay. And other stability analysis, they can be compression and crushing. Dam may fail by the failure of its material. Its material may have, because they will be acting, so it should be able to, the concrete should, the compressive strength of the concrete should be able to withstand the loads that is allowed. So the compressive stress may exceed the allowable stress, and the dam material may get crushed. So concrete has very high compressive strength. The tensile strength is low. As you know from, I think people with civil engineering background must have studied this. But anyway, this is something that is important. The other thing is the tension. The concrete gravity is designed in such a way that no tension is developed anywhere, because they have very low tensile strength. They cannot withstand a lot of tensile stresses. So concretes and masonry dams don't have, concrete don't. So that's why you have reinforcement. If it is subject to such stress, these materials may crack. So the compressive stress and the tensile stress should also be calculated. So basically, these are the important parameters to be considered when you are designing or considering a gravity dam. Okay, so if there is any quick question, I can take for 1 or 2 minutes. Otherwise, I will move to another topic uh, on earthen dams, earth dams. Carlos, any quick question or I can move?
Thank you, Divas. Haverá alguma questão, algum comentário, por enquanto? Antes de prosseguir para a última parte desta manhã. No, I don't think there is any question.
Okay.
Divas? Yeah.
Okay. Yeah.
I want to make one question.
Yes, please.
It's about the sedimentation evacuation facility in a dam. We have seen in the past and even here in the region that many dams are being affected by siltation. What do you propose for dams that didn't have any plan to evacuate silt, or what solutions do you see for those dams?
Yes, I think, thank you. I think it's a very important and a good and difficult question also. The reason I say this is you are very right, because if the sediment load in the river is high, when you have a dam that obstructs flow, all the sediment will be accumulated in this reservoir area. And there is, maybe I'll cover in one of those sessions later, that there will be a sediment load which can cover the whole load. From my experience a little bit and from the literature that I have gone through and from the information I have, there are 2 or 3 ways how you can manage that. Number one is most dams have what they call a dead storage area. Okay, so they have the total storage area is the gross storage, and the dead storage is maybe 25–30% of the storage area is reserved as dead storage, and live storage is only the remaining part. And this dead storage in some ways are designed to last for 50 years, minimum 50 years, where the dead storage, the sediment will be filled in the dead storage. In the dams in Nepal, for example, we have this dead storage, and the calculation of the dead storage design is at least the dead storage should not be filled in 50 years by sediment. Okay, but from a sustainability point of view, what will happen after 50 years? No, that is the question. So you have to, just a moment, I received a call from Carlos. Let me just, hello, Carlos? Hello? Hello, Carlos? Hello? Carlos, can you hear me? Hello? Hello, Carlos? Hello, Carlos, can you hear me? Hello, Carlos?
The system was down.
Okay.
Yes,
Now
the system was down. You have to restart.
Okay.
You have to restart.
So,
yeah.
Okay. Can you hear me now?
Yes, properly.
Okay, thank you. So as I was saying, so one is the dead storage, but after 50 years, the dead storage will be filled. Then you have to do a decommissioning of the dam. So after 50, 60 years, the dam will not be functioning as it should be, number one. Number two, I think to really, dams have these problems. To really reduce the dam, you have to do watershed, the catchment, you can control by watershed management conservation. So you have check dams upstream so that you don't let the sediment come all the way to the dam. So this is more of software thing instead of really building, and you can have check dams along the catchment. So and these type of catchment improvement programs are done by the country and by the dam authorities also. So you try to reduce these flow into the sediment is number two. Number three, I mean, I admit that I do not have too much of experience, but I have heard that you can have dredging. So you can have dredge the sediment that is filled and use for as construction material and take it out. But that is a very expensive proposal to take the dredging of these sediments from the dams. Number three. Number four, it is very difficult, but you can have some flushing. You can have an opening in the middle of the dam and you can do the flushing of the dam. But now the pressure that will act here and the flushing, it's a very tricky hydraulic design. So for very high dams, this flushing of the draining the sediment is very difficult as far as I know. But there is one project in Nepal where it's a relatively, I think, I don't know, 80-meter dam or 90-meter dam. They are proposing that during the wet season, they will have some flushing. And some people also have bypass tunnel where you can do the flushing of the sediment. But these are very complicated design proposals. And I don't know how successful they have been, but they have been plans like that. So, but sediment management is a big issue for dams, and there is serious criticism by environmentalists and social organizations of dams, considering the problems dams face with sediments. I don't know if I was able to give you a very clear answer, but I think these are the options available, and this is the problem. This is what I wanted to say.
Yeah, thank you very much. It was very good to hear. Yeah.
Yeah, thank you so much. Thank you so much. And I would be very happy to sort of interact and learn from, because I am interested to learn a little more so that what is the sediment load in Mozambique rivers. I will maybe through Dr. Carlos and other colleagues, I will interact more with the participants, with different organizations. And let's try by the end of this capacity building, if you could take up some cases in Mozambique, some case studies on sediment management and other issues, that would be very interesting. Thank you so much. Yeah, Carlos? Hello?
It's 12:30.
Yeah, it's 12:30. So maybe I will stop here, but I will take, tomorrow I have a class in the morning. I'll try to make up. So I will take from Earthen Dam from tomorrow, okay? And then also I will do some hydraulic machines and equipment tomorrow, okay? So thank you very much. If there is any question, we can take it now, or we can, tomorrow morning, we can discuss again. Thank you so much. And I hope I was not too fast. So please let me know if it is difficult to understand me. I admit that because of some issues with the internet, there has been some disturbances, but I think it was very kindly, quickly resolved by colleagues in the university in Mozambique, by Avelino and Dr. Carlos and Avelino's team, Dr. Avelino's team. Thank you so much.